Namaste and welcome to this lecture on linear algebra through geometry. In the past couple of classes you would have studied about solving system of equations through Gauss elimination method, getting to the reduced row echelon form, where we did a lot of elementary operations and we got to the a matrix which was simple to handle, from which we could pull up our the values for the unknowns. And we also looked at some of the insights to the what actually happens when you do this elementary row operations and stuff, and how do we implement, how do we carry out these elementary row operations on let us say a given matrix. So you have to, you saw that when you went from the given matrix A to the row reduced echelon form of the matrix A, you carried out a series of you probably had multiple elementary row operations. At every stage you ended up doing one elementary row operation, you went to the next stage and again you found something there, you did another elementary row operation and so on. So you basically had a sequence of elementary row operations, which means at every point in time we were trying to do matrix multiplication to effect that particular row operation, right. So we had a sequence of what would you call as elementary matrix multiplication with the transformed matrix in the sense, okay, I had the first augmented matrix where I had A and B, and then I did some row operation on that, and then I got my the first iteration. At the end of the first iteration I had something else, I found something else there, so I wanted to make that pivot entry, the pivot below the pivot element, I want to make the other fellow 0, so I ended up doing another elementary row operation that again got carried out in terms of matrix multiplication and so on. So we basically did a sequence of elementary row operations to get to our solution, and in fact that is exactly where we defined the idea of equivalent systems also. We said that, look, okay, two systems are said to be equivalent if they have the same solutions and so on. And after that what we did is we started looking at the idea of matrix inverse, right. What is it to say matrix inverse? And we also had a good idea about determinants and properties of determinants and so on. So the question is, like, what is this matrix inverse? Why do we even want to look at inverse of a matrix? And that is something very interesting. Mathematically you already know what the inverse does. If you have let us say Ax equal to B and assume that A is a square matrix and n by n matrix, that is exactly what you would have done in the previous class by Professor Krishna Kumar. You would have studied that, okay, if you have a matrix A n by n, it is a square matrix, and if it is invertible you found the inverse of the matrix to be adjoint of the matrix A divided by the determinant of the matrix A. Therefore the idea of determinant comes into picture. So you look at what is determinant and how did how is the determinant an important thing as far as finding the inverse of the matrix is concerned, right. So if the determinant since it says A inverse is equal to adjoint of A by determinant of A, we said that, look, if the determinant of A is 0, then you can't really find the inverse of the matrix. That means the matrix inverse doesn't exist, and you call that matrix to be a singular matrix. So these are things that you have done before. Now what we will do is, if you are going to look at why would we want to even study the idea of inverses? Why can't we just mathematically do it as like, okay, Ax is equal to B, A is a square matrix, invertible matrix, therefore x is equal to A inverse B. So why don't we directly do this math and then do it? Now thing is, we need to if we understand things conceptually, then it allows us to get a grip of the subject. So what we try to do is we try to look at the problem of Ax equal to B from a completely different perspective and then see what happens, right. So that is exactly what we are going to do today as far as the inverses are concerned, right. We are going to look at inverse. I think quite a bit of thing has been done about determinants, how to find determinants, what are the properties of determinants. You've done all that, and what we're going to do is just going to focus on this topic of inverses today, and we will come back to this determinants again from a geometric perspective at a later point of time, and we will keep the interest on till we get to the vectors, vector spaces, and this determinant idea. We will keep that for the vector space of clubbing the idea of determinants in with vectors and stuff. So we will just take it a bit later for more insights, but what we are going to do is we are just going to look at inverses now, right. The properties of determinants have all been done. You had the list of things you had, like A transpose inverse is equal to A inverse the whole transpose and so on. You have, if you have A and B to be matrices which are what do you call invertible matrices, then you had AB the whole inverse is nothing but B inverse A inverse, and that also got us to that point where we had, if you have sequence of elementary operations like E1 on the matrix A, then E2 on the matrix which is obtained after applying E1. So E2 into E1 into A, E3 into E2 into E1 into A, and so on. You try to get the inverse by saying, look, yeah, I can invert each of these elementary row operations that I have done, but I have to do it in the reverse order. So if you have that is exactly what I said. When you if you do A into B, the inverse of AB, the product matrix C is equal to AB, C inverse is nothing but B inverse into A inverse, right. So that is exactly where we got into the idea of, we understood the properties of inverses and lot of determinants and stuff. So what we do is, let us just try to focus on the system of equations where we have n equations, n unknowns, and then let us try to understand why this inverse matters. So let us go ahead. Consider Ax is equal to B, where Ax equal to B is a system of n linear equations in n unknowns. Now first of all, let us understand what this means. Assume that the matrix A is a real matrix, B is also a real matrix, X is going to be a set of real numbers that we are looking at as the solutions for the system of equations. Now first of all, let us focus on this. It is basically something which has n linear equations and n unknowns, which means A is a square matrix of dimension n by n. The number of rows is equal to number of columns, and therefore X, there are going to be, it already says X is basically you have n unknowns. So this is going to be n by 1, and that is going to give me B, which is also n by 1. Now essentially what we are saying is, consider, suppose if you already said that it is a system of equations. So what I want to do is, I want to consider this A itself as a system, right, A n by n as a system, to which I give this input x n by 1 and I get my output B, which is n by 1, right. So this is basically the system that we are considering right now, system under consideration. System under consideration. So what does it essentially mean? So how do we interpret this? So what we say is, okay, these are all my inputs to the system, and these are all the outputs from the system. That means you excite the system with these inputs, that means X is also called as the excitation, and B is basically the outputs, basically which correspond to the response of the system for this set of excitation or inputs. So what are we trying to ask? We say, when we say solve for the system or solve the system of equation, when we say solve the system of linear equations Ax equal to b, what are we trying to tell? What is the interpretation or what is the meaning that we have? We say that look, I have a system, I have the output from the system, but I really do not know what is the input. Find out the input, that is exactly what we are looking for. For this system A, I give some input which I probably do not know, and I see at the output this is the output B that I get. So the question is, tell me what is that input that I had given to get this output B from that system A. So the interpretation here is saying, given the system and the output, given the system A and the output B, find that input which made A give this response B, that input, let us say x, which made A, the system A, give this response B. Right, that is what we say when you explicitly state that solve the system of linear equations. Now, how do we solve? So the question is this, okay, I have, as usual, I said this is A n by n, and this is x n by 1, and this is B n by 1, right. Now, how do we get the value of A? If you look at it in terms of systems, how do we get to the value of A? Let us take a simple example. What is that? Let us consider the simple example. So let me say y is equal to 5x. Let me say y is equal to 5x, right. Forget about this is not a matrix, this is just a scalar, this is just another scalar, this is another scalar. Now what it says is, okay, any input that you give as x, the system is going to multiply by 5 and I am going to get the output y, which is equal to 5 times x. So this is what I am going to have, 5 into, I will put so that it says 5 into x, right. Now what I do is I am going to give a simple thing here. So I am going to say, look, from this system the output that I had was y is equal to 10. So I had 5 times x, the output was 10, which is equal to y is equal to 5x, and I ask you this question, what is the x that I gave here, right. That is easy to say because you have 5x is equal to 10, and what did we do? We said x is equal to 10 by 5, which is basically 1 by 5 times the output, right. Now if you look at this, when I say 5x is equal to 10 and x is equal to 10 by 5, and so this is going to be the value x is equal to 2, there is something interesting that happens here. What is that? All I did was, whatever the system was which was 5x, I took the inverse of that system, which is 1 by 5, and then I multiplied that output with that inverse of the system, whatever that function that I have, which was 1 by 5, and then I got my output 2, right. That is what we get. Now the question that I have is, can we do something similar to that here? If the system is as simple as this, it scales the input, whatever input that you give, it scales the input by 5. I could say that, okay, y is equal to 5x, the moment you give me the value of y, I can always give you the value of x, because x is equal to 1 by 5 times y, right. So given y, we can always find, as I said here, x is a real number, let us take x as a real number, y is also a real number, let us put all that, okay. So we can always find x is equal to 1 by 5 times x. I mean 1 by 5 times y, right. That means given y I can find out x. Now if you note something very subtle here, our input output relation for the system was y is equal to 5x, and here what has happened is I see x is equal to 1 by 5y, and these two are essentially, these two are similar, they look very similar. Now what is it that they look very similar? Let us look at that. So when I was talking about this 5 times x with the input x and I got my y, the output was y and the input was x, and our quest was to find the value of x for a particular given y, right, for a particular y. Now what I did, so this we said y is equal to 5x. Now what I am going to do is, no do not do this, I want to find out this input, and that in order to find out the input, let me look at the problem in a different way. What do? I give y to this system as input, where the output is going to be x. Whatever was the input that I had here, that turns out to be the output from the inverse system. This is the inverse system of this guy, right, it is the inverse system of this guy. So what did I do? Basically whatever y was the output that was available to me as y is equal to ax, what did I do? I gave y as the input to A inverse, and whatever was the input that I had for ax, I had to find out that became the output for the system x is equal to A inverse y, right. You are going to have x is equal to A inverse y, where let us say A is not equal to 0, A is a real number and not equal to 0. Whenever you have y is equal to ax, you can always find x is equal to 1 by A or A inverse y, where A is not equal to 0, right. That is a simple trick that we have. So now the question is, can we do something like that with matrix also, right, and that is exactly where we get into the idea of this inverse. So given a matrix A, the question is, okay, let me move it as given a system of equations Ax equal to b. So let me do this, given a system of linear equations Ax equal to b, where A is Ax equal to a set of same, we will use the same thing, a set of n linear equations in n unknowns. Right. Can we find x for a given b? So the problem now translates to saying, look, I have this, the matrix A, which is n by n, to which I give this x n by 1, I have b. So the question was, find x. This is given and this is also given, right, this is given and that is given. So find out the value of x. Now how do we tackle this problem? You do this, instead of looking at this problem as Ax is equal to b. Now what we do is we look at, you have this system A inverse for which you give this input as b, and then look at x is equal to A inverse b, right. The problem basically transforms to finding out the output from a system for which the input is basically b. Is that right? So the question is, okay, so this is what we need. So you reformulate the problem as find the output of the system find the output of the system A inverse corresponding to the input B. To the input B. That gives you another set of linear equations where in which we have x is equal to A inverse B. A very quick look at your what would you call the set of equations, two linear equations and two unknowns will reveal this. Let us just quickly do that. So, let us assume that we have a11 x1 plus a12 x2 is equal to b1, a21 x1 plus a22 x2 is equal to b2. This is what we have. So, I will put this matrix here A, which is equal to this coefficients a11, a12, a21, a22. We have x1, x2, and this is the output that I have, which is b1, b2, right. Now, let us try to we know how to solve this system of equations. It's pretty easy to solve. So, what I will do is I will follow the high school technique of eliminating one of these variables. So, you have a11 x1 plus a12 x2 is equal to b1, and a21 x1 plus a22 x2 is equal to b2. This is what we had. So, let me call this as equation 2 and call this as equation 1. Now, what I am going to do is I am going to eliminate let us say x1 from equation 2, eliminate x1. So, what am I going to do? How do I eliminate x1? So, I am going to do this, I am going to do this, I am going to multiply equation 2 by a11 and I am going to subtract it from the equation 1, which is going to get multiplied by a21. So, I will get a11 a21 x1 plus a12 a21 x2 is equal to b1 a21, and then I am going to get this a11 a21 x1 plus a22 a11 x2 is equal to b2 a11. So, I am going to subtract this guy. So, I am going to get this. So, this gets knocked out. So, what I have is x2 into a12 a21 minus a22 a11 is equal to b1 a21 minus b2 a11. I will just do a small rearrangement here. I am going to write this as x2 is equal to b2 a11 minus b1 a21 divided by a11 a22 minus a21 a12. Similarly, you can look at the value of x1. If you try to sort, I am quite sure you would have done this in your previous lecture. You will see that x1 is nothing but b1 a22 minus b2 a21 b2 a12 divided by a11 a22 minus a21 a12, right. This is what we have. Now, we have got the values of unknowns, but how are we going to say that okay, where is the inverse system and all those things. So, let us just look at this. So, I am going to have x1 x2 x1 x2. I think the denominator, if you see clearly, the denominator is the same. So, I will write this as 1 by a11 a22 minus a21 a12, and what do we have with the numerator? At the numerator I have a22 b1 minus a12 b2, and I have x2, which is nothing but x2 is a11 b2 minus a21 B 1 is what we have. Oh, still we do not see the matrix form like what we had, x is equal to A B A inverse B. So, let us see what happens there. So, I have x 1 x 2 is equal to 1 by, we had this A 1 1 A 2 2 minus A 1 2 A 2 1. If you look at this, I can do something like this. I can pull out my B 1 and B 2 here, and what do I have here? I have A 2 2 minus A 1 2. I have A 2 2. A 2 2 was multiplying B 1, A 2 2 minus A 1 2, and what did we have here? A 1 1, and this basically was A 2 1 B 1 minus A 2 1 B 1, and you had A 1. So, let us look at this, minus A 2 1 and you had A 1 1. Now, this looks like a matrix. You have this matrix here, you have some scaling here, and then you have this of the form B. So, what we see is, we see this is going to be 1 by A 1 1 A 2 2 minus A 1 2 A 2 1 into this matrix, which is A 2 2 A minus A 1 2 minus A 2 1 A 1 1. If you give this B 1 B 2 as input to this system, you get the output to be the corresponding x 1 x 2, and this is what we call as the inverse of the system A, which is actually dependent on the determinant. If the determinant is 0, then we say that the inverse does not exist. So, what is it that we see here? What we had was the original problem, which was A x equal to B, for which we need to find out the value of x for a given B. We now reformulated this problem as, look, give B as input to A inverse system, the output that you get is corresponding x that you are looking for, provided this inverse exists. So, the idea of inverse system helps us a lot, but only problem is like finding the inverse for larger matrices is going to be major issues, like instant, I mean finding the determinant, and you do all this cofactors and stuff. It is going to be a bit computationally intensive task for larger matrices. So, we look at other approaches. So, what we do is, we will wind up here, and in the next class when we come, we will look at in detail. We will also get some insights about determinants, and we will also get some insights about Cramer's rule. Thank you.